All right, so today we have a presentation by Tushun on state space models, which are compared with the transformers. And he will also present the two works that apply in the green language.
So, hi everyone, I'm Tushing, and today I'm going to talk about the hotspot of the recent few years, the state space model. And it claims that it can combine the best of both worlds from the recurrent neural network and the transformer, which are the two models that people are widely using in like large language model, like and other sequence modeling tasks. So yeah. So talking about the sequence modeling task, it is a task that a technique that machine learning uses to analyze and predicting patterns in the order data, like text generation, like in machine translation, like predicting the market prices. And yeah, so it applies where the sequence of the data, the order of the sequence data matters. And naturally, the model needs to remember the past, like the context to predict the future. And this is called the long-range dependencies, and that is the crucial part in the modern large language models. However, the current models like recurrent neural network and the transformers are either very easy to train but slow to infer, or it is fast to infer but hard to train. So for example, this is a typical recurrent neural network. It maintains a hidden space, and when given an input X, it will process the information of the input, and given the hidden space, it will output as Y at time t. So the benefit of recurrent neural networks is that they are easy to inference because they scale linearly with the sequence length. That is because of the benefit of that fixed compressed view, which is the hidden state. So the model uses only this hidden state to do the inference, unlike other models. However, the downside of RNNs is that they are hard to train because it is a purely autoregressive model, so that it cannot be trivially parallelized. Another problem is that when we are training the model, because it is sequential, when we're making some mistake, and like in this example, the model is trying to predict the next word. At the very end of the model, it predicts something, and you need to back propagate that information to the very start of the model. That leads to vanishing gradient because the sequence is just too long. The model tends to forget information over time in the RNNs. And there's another series of models called the transformers. They use a revolutionary mechanism called the self-attention to get the information of the context. So the self-attention basically works like it's a weighting technique that measures the importance of two words in the context. Like in this example, my name is Martin. Then maybe name and Martin should be their relation should be more important than any other combination of the words in the sentence. Transformers are easy to parallelize training because the transformer sees the entire sentence at once, and the self-attention matrix, the square matrix, can be computed in parallel, and that is very hardware friendly for modern GPUs. However, when doing the inference, transformers are notoriously taking so much space because it needs to just compute the self-attention matrix, and that space is growing quadratically with the sequence length because every token needs to look at every other token. There has been works to shrink this self-attention matrix, like by taking only the necessary attention between tokens, but that doesn't solve the problem at all. So that is how the transformer and RN are failing to do the job. And yeah, I'll enter the background of the state space models. So the content after this is pretty math intensive, so please just interrupt me if you don't understand anything. So state space models, one person, Albert Gu here, he is pretty much the pioneer in the modern state space models. He introduces
The guy from the neural model introduced the concept variability of Elias.
like yeah.
And this builds then on this.
Yeah,
concept.
yeah. Albert Gu, he builds upon those concepts from 2020.
Yes, but it was
yes,
with
yeah.
Elias.
Yeah. And this person, he introduces the S4 model and the Mamba, which is the pretty much the what people are using for state space models. So what is a state space? The state space is a space that contains the minimum number of variables, what we call the state variables, that fully describe a system. So for example, you are a car that is navigating through a maze. Your state can be fully described as the x coordinate, y coordinate, and your distance to the exit of the maze. That three tuple, that space of the the xy, and the distance describes a state space. Another example can be like a pendulum. Its angle to the vertical line and its angular velocity fully describe this system, so that it's a two-state variable state space. And state space models, instead of looking back at every single past input to make a decision, the SSM only uses the current state that condensed all the information from the past input to make a decision. It all starts from the continuous form. So yeah, SSM is defined as a function-to-function transition instead of just a like a sequence discrete signal transition. This is just the only two functions that defines a state space model. It's a first order ordinary differential equation that measures the first equation measures the change of xt, which is the state space. Is there annotate over here? Yeah. So xt here is the state space. This is the vector that describes the state, the space. And ut is the input signal. Beware, xt and ut and yt are continuous in this case. And a, b, c, d are transition matrix so that the a controls how the state itself evolves, and b controls how the input affects that state space. And c, based on that state space, how that translates to the output yt.
These things come from Paul.
Yes. Yeah. And it's somewhat similar to recurrent neural networks. However, recurrent neural networks has a 10H nonlinear activation. And that is not the case in the state space model, which gives SSMs a very beneficial property, which I will introduce later. So in general, it's just a system that maps a 1D input signal ut to an n-dimensional latent state xt, and then projects it to a 1D output signal yt. And all the four transition matrix A, B, C, D are learned by the gradient descent. Now, when we are trying to apply that continuous form state space model to a discrete signal, like the sequence modeling, which involves tokens so something like that. we need to discretize the entire system. So X, K, and UK here are discrete input sequences instead of functions. So this entire thing convert from the function to function mapping to a sequence to sequence mapping from input UK to output YK. And this, the A bar and B bar are the discrete form of the previous continuous form of the ABCD. In this case, it is discretized by linear discretization, but other forms also exist. The takeaway from this is that by discretizing the entire system, the continuous ABCD matrices will be parameterized by the delta here. The delta is the discretization step size, which you can also view as a sampling rate. The important thing here is that we can arbitrarily set this sampling rate. So state space model in general can work in any frequency. Unlike transformer or RNN, which is defined directly in this discrete form. So this discretization form allows us to use the SSM as an RNN, which we can leverage their fast autoregressive inference. So now one problem is solved. The inference is fast for SSM by using the discrete form. But we still have a problem with the training because that is still sequential. Any problem here? Any question here? Please ask.
Delta B.
That is just multiplication. The delta. The delta itself is a parameter. Like you can set, you can set it like 10 hertz or 20 hertz. It's just like a sampling rate from the continuous form to the discrete form.
Sorry, sorry to interrupt. I just want to know, because the state space models is widely used, right? For example, in a control, for example, when you are doing Kalman filtering, you can just reformulate the problem using state space model. So is it a really unexpected or really new contributions when people introduce the state space model to I don't know, whatever network you want to train?
I think basically introducing it into the neural network, that's the contribution. So it's around, yes, it is around for control forever. But implementing it into a neural network, that is the novelty. Nobody has used it in a network before.
So it's like you are interpreting the network as a dynamical systems, right?
Yeah. So when it's used in application, like the normal input would be just words, like the output, and the output maybe to predict the next word. It's just applying this system in a sequential modeling problem.
Okay, thank you.
In some way, it's like a recurrent neural network.
It is.
With a long memory.
It is.
Just last one, but can remember as many as you want, 23 or so.
Yeah.
But there's no nonlinear. So I have less representation of capacity.
That's true. That's true.
There's no signal capacity.
But the linearity also gives us very important properties that will in the next slide. The most important thing that how we can train a state space model so efficiently is that it has a convolution form. You see, this discretization form is a linear time invariant system. The linear just means there's no nonlinear activations here. And the time invariant part means, why there's no D here? You see, in continuous form, there is a matrix D that acts like a skip connection directly from the input UT to the output YT. and is often discarded or omitted in the discrete form because that is easy to implement. So there's no need to add that matrix D into the formulation. So back to the time invariant part. The time invariant means A, B, C are fixed after the training. So during inference, they do not change, which is how normally model will behave. Like they fix the parameters when doing inference. And this LTI, linear time invariant system, we can expand it. Like we write out the element, the x0, x1, x2, y0, y1, y2, and you can observe that there's the coefficient before that input is just a multiplication of the ABC matrices. And more importantly, it's just a C bar times the powers of A matrices, and then one B bar matrix. By observing that, we can write it in a very nice form, like with a discrete convolution with a kernel defined by K bar. So the kernel is CB, CAB, CAB, CAAB. And that is convolved with the input to get the final output Y. I will show you a nice visualization how the convolution works. So above here, it is the kernel. Right now, it is only 3. And in the middle, it's the input padded by zeros. So when the kernel shifted through the input, it computes the element-wise product that yields the output. So that, see, y0 here is computed by 0 times here, 0 times here, and x1 times CB. That is y0, and y1, y2, etc. And why this convolution is so beneficial? It's because it can be very efficiently computed by fast Fourier transforms. And it directly reduces the computation complexity from big O L squared to big O L log L. And why? Because the convolution theorem states that the convolution in the time domain, where that is what we at now, is equivalent to the element-wise multiplication, which is cheap in the frequency domain. And this element-wise multiplication can be easily implemented on the GPUs that enables parallel training. So that's how the convolution form of the state space model enables fast parallel training on GPUs, unlike RNNs. Yes.
Oh, A raised to K can vanish or explode depending on the eigenvalues of A.
Yes.
Right? Do you have to do something like some constraint over there?
Exactly, yes. Yes. So the matrix A is very important because the observation is that there include many powers of A, which depending on the eigenvalue of the matrix A can lead to gradient, what is it? Exploding, exploding or vanishing gradient.
Just the gradient, even YK, right? Because
Yeah.
you are like just even the input can explode. Like I think one of the reasons in RNN they had tan H was to get control of X.
Yes. So before we tackle that problem, I want to make a summary of the background of the state space model. So what state space model is doing is trying to first define it in a continuous time domain. So that like matrix A is controlling the evolution of the state space, the hidden space. Matrix B is given controlling how the input is affecting the state space. And C controls how that hidden space translates to the output. And D, normally it is implemented as a skip connection. Then by discretize it, we can have two forms. The recurrent form ensured us efficient inference because it doesn't have memory issues like in the transformer. So we can just do fast auto-regressive inference. The other form, the convolutional form, ensures us parallelizable training. So it kind of combines the benefit of the RNN and the transformer, both excel in the fast inference and fast training. Okay, and this all happens before S4. The S4 is introduced in Albert Guth's paper, essentially modeling long sequences with structured state space. And for the S4, the naming stands for structured state space sequence model. So there are 4 S's here. And in this paper, they tackle the problem that, like the matrix A, how to design smartly the matrix A so that the gradient does not explode or vanish. The A bar matrix, which is the discretized form of the A matrix, is one of the most important, if not the most important thing in the state space model, because it captures information about the previous states and it builds the new hidden state. But however, the linear first order ODEs have solutions involving the exponential function, which what that means is that the gradient will scale exponentially regarding the sequence length. And if the eigenvalues of the A bar is slightly smaller than 0, the signal or the gradient will vanish. And if it's slightly larger than 0, the signal will explode. So if we do not do anything about the A bar matrix, the model will not be able to learn long-range dependencies. So the S4, it's not directly introduced in S4, but it's in the same author's paper, like in 2020, like 1 year before the S4 paper. That is called the Hippo theory. It's essentially how to guide us how to design the A bar smartly. The Hippo stands for high order polynomial projection operators. What it does is so given an input signal, we want to compress it into like a fixed size of states and hope that these states can be reconstructed back to the input signal so that all the information about the input will be compressed in that fixed amount of states. So, maybe I should pause here. Any question here, like how Hippo works? Okay. So in the S4 paper, they designed a Hippo matrix that looks like this. And if we write it out as a 4x4, it looks like this. So what this Hippo A matrix aims to is to optimally compress the input, the history of all input signals into a fixed size factor, which is the state space, XT here. And as a visualization, the Hippo matrix just treats the state variables X as coefficients of a Legendre polynomials. So here, the red line here is our input signal, and the black histograms represent our X case, which are the coefficients of a Legendre polynomials. And the black lines are the Legendre polynomials. So from the X case, we can reconstruct the input signals, which contains all history of the inputs. That's how the vanishing or exploding gradient problem is circumvented over here. So the takeaway from the Hippo theory is that in S4, the Hippo is used to smartly initialize matrix A bar. It's very similar to like timing or other initializations for neural networks. It just tries to stabilize the SSM system so that it is mathematically stable, and we can so that ensures that it's mathematically stable. And after that, we can like train on that matrix. So this single design, the Hippo theory design, boosts the accuracy on the sequential MNIST dataset from 60% to 98%. The sequential MNIST dataset is just like big MNIST are digits, so the sequential means that it gives the coordinates of those strokes. So that as a sequence of to represent the MNIST dataset.
But you have to decide on the size A before.
The size, yes. So A also controls how large you want the state space to be. So
But you're not going to decide.
Yes. So any questions here?
So in that A matrix set, I think it was in the previous slide or something, or another slide. So is it like upper, like lower triangular to ensure like easier computation of A raised to N or something like that?
Sorry, Elias.
Like, why is it like lower triangular over here? Like, is it to enable like faster computation of powers of A or invertibility or
somehow they found that this converges, right? I think it comes from some knowledge in policy, but I don't know exactly.
I don't exactly know.
Yeah, it means that. Yeah.
Oh, so even in control theory, they use it.
Yes.
Mm. Yeah.
But I don't know what the large problem is.
I think computing powers is much easier. All these matrices, even converting the inverses, are very easier with these. Computing the Jacobians is also very easy. So I would ask like for which of these reasons? If it's no in control theory, I probably just whatever reason they do this one.
Yeah. So the Hippo just try to ensure A is well initialized, but we still need to compute the powers of A. One way to do that is by diagonalization. So if we compute just naively the powers of A through L successive multiplications, it will be O M squared L complexity, which is very, very expensive. So suppose we can diagonalize A bar and assume B bar and C bar are vectors just for single inputs. The A bar, it can be diagonalized into the form of matrix A times the lambda times the inverse of matrix V, where the lambda denotes a diagonal matrix, where the diagonal is just contains the eigenvalues of A matrix. If that is the case, if A is diagonalizable, we can rewrite the kernel into the following form, which is kind of ugly, but if you follow me, the first element of the kernel, K0, is computed by like 1 times C1 B1, because C and B are just vectors, not the matrices. And in this case, because A is diagonalizable, so we can just multiply their eigenvalues to the matrix C times matrix B, so that we can compute the powers of A very efficiently. This matrix is actually what is called a Vandermonde matrix, which enjoys the property of computing the matrix product very efficiently. I haven't looked into this in detail, but this is what the case. And the van der Waals product enjoys O n plus L times the log of the sum of n plus L complexity, which is much faster than naively computing the powers of A.
Sorry, maybe
Yes.
I missed something about the dimensions, because when you say that if A bars can be diagonalized, so you suppose A is a square, right?
Yes.
Otherwise, I think you suppose you're going to do the SVD to have the equivalent of your eigenvalues, I suppose.
Yes, you're correct. I'm assuming the A bar here is
Squared. Otherwise, you can
square.
diagonalize. Yeah. Okay.
Yep. Okay. However, the Hippo matrix is not diagonalizable, because by diagonalize the Hippo matrix, one entry in that Hippo matrix, which is the A matrix, has an entry exponentially large. Specifically, it is 2 to the power of 4n divided by 3. And n is the dimension, the state space dimension we want to encode the input in. So that if you want to encode the system into a 64-dimensional state space, which is pretty small, the entry will be as large as 2 to the power of 4 times 64 divided by 3, which is already exceeding the maximum value of float 32. That renders huge numerical instability. So diagonalization doesn't work. However, the authors of S4 paper found out that the Hippo matrix can be decomposed into a normal matrix plus a low rank matrix. So the normal matrix can be diagonalized, and we just need to find a smart way to how to deal with the rest of the low rank matrix. And this sentence I just summarized from the paper. I don't intend to go into the math details because they're so hard. So instead of computing directly the powers of A in the time domain, it essentially in the S4, they're calculating the generating function of the kernel and evaluate that function at the roots of unity. And after that, the kernel can be retrieved by applying a inverse Fourier transform. I don't fully understand this part, but in general, it provides a way to circumvent the computation of powers of A into the computing a inverse Fourier transform.
Yeah, roots of unity is like e raised to minus j, k omega or something, and then you find like the different roots which
to evaluate those roots on the frequency domain.
Yeah, like you convert frequency domain getting into. So I can see how this works, not exactly, but.
And surprisingly, the tutorials online are all of them are not talking about this part. They just give
X raised to n equal to 1 if that's the one, and if you can have complex numbers, then how many roots of unity can you like one, like the nth root of 1. I don't exactly remember this, but there is a decent amount of theory. And to go into complex numbers, you go into the frequency. And then you can write everything as e raised to j k something.
Okay. So the takeaway here from the diagonalization of matrix A bar is that despite it is not normal, the Hippo matrix A is normal plus a low rank matrix. So it's called NPLR by the authors. And they prove that there's a nice and efficient way to compute the kernel from the NPLR matrices by not computing the powers directly. Okay, so in general, S4, it's defined firstly as a continuous state space as like any other state space model. And it smartly designed the matrix A so that it can handle long-range dependencies and provides a way to compute the powers of A so that the kernel can be easily computed. And after that, that can be discretized as the recurrent form or the convolution form. So S4 paper basically provides the mathematical foundation we need to efficiently use the state space model. I'll pause here. Any questions?
It's very interesting that they didn't have to use like multiple layers like in deep learning. Like for transformers, like you have multiple layers.
Oh, they do. They have like multiple blocks of SSN. You mean
each, but they don't use any non-linearity. Like for any XT, you just have one A times XT layers, like not a succession of many layers.
Yeah.
Okay. So I think that's interesting.
That wouldn't help you much, right? If you just start doing variables. You could do it really quickly.
Yeah, but it seems to work.
Yeah.
So,
And what is the essence of hippo different from
the hippo? Oh, the hippo.
or hippo is a sport?
The hippo designs the A matrix and the this
lower there.
and this provides this is a way to compute the powers of A. And hippo designs A.
Quick question. You said there are multiple layers. Like, where are these layers? Like, or
I mean, multiple blocks, like one after another.
oh, the time blocks? Or
like
the blocks with respect to time? Or what kind of?
Like this is a block, and after this, you connect another.
Oh, yeah. But so it's like in time.
Yeah.
Like as you go in.
Yes.
Yeah.
But they have the same A.
What do you mean, like?
You computed UA. I mean, you said multiple time blocks.
No, I think the A's and all of those are carried across the time. Yeah, same.
And each block has all-to-all connected units, right?
What do you mean by all-to-all connected?
Like that's the state space. Like the X is represented by those. I don't know if you want to call them neurons or like those are the units, right? That make the block, or that's not how. Like so that represents the recurrent neural network, right?
So the input is the U.
Input is U.
The X,
yeah.
Intermediate representation can vary. The Y the output.
Yes, Y the output.
And all use of a certain length defined by the matrix A, right? How long connect to X. And
A
powers of A. Yeah, like
I mean,
you
you
have
have-
A raised to K, yeah, it depends on like K steps behind how much do you remember that?
Right, but that is, I mean, but obviously A and A encodes the length of how much you remember, right? So it can be an LSTM, it's just one layer, but plus nonlinear.
Yeah.
And in the state space models, it could be the whole image
Mhm.
in blocks, usually.
Yeah. Yeah, if you design A such that it can actually remember absolutely everything and does not decay too much with respect to the powers, then I think it can.
Yeah, so the hippo solves the decay, the problem.
So how do they use it in images and or video sequences? What would be then the A? And what would be the parallel management?
Well, I think it's similar to how VIT works. It's just by into patches and
And then the A contains all the patches of the image.
No. A is the parameter. It does not contain anything from the input. So A only applies to the hidden space. So it controls how the state space evolve.
For each batch you compute one Y.
Yeah.
Y or one X.
Yeah, and A is
And you
fixed.
shift it along. So for each batch. If you use it in space, but the best computation is in time.
And then in S5, I don't know if you're gonna talk about S5.
Oh, no.
They take, they just come up with a way of making this more, making it more efficient to do multiple state-space models at a time. So that you can apply it to every patch simultaneously. You can have one model for each patch.
Oh, nice. Then we're talking about Mamba. Mamba is often called the selective state space model, but it has another name, S6. The selective scan structure state space sequence models are the hence. So therefore they give it a name called Mamba because they're so acids, so it sounds like a snake hissing. And this paper is published in 2024 by the same person. So what is the problem with S4? S4 is a linear time invariant system. And that is the only reason why S4 enjoys both recurrence and the convolution properties. That means ABC, the parameters ABC are time invariant and they're fixed during inference. So intuitively, the LTI SSMs lacks the ability to focus on or ignore, basically filtering particular inputs. So in the Mamba paper, the author presents two specific tasks that S4 will fail on. The first one is called the selective copying task. It is a modification from the standard copying task. The standard copying task states that you have a input containing a successive colored blocks that represents useful information, and the white blocks which contains no information. And the task is to just replicate all the colored boxes as a output. So the S4 can do this because it is using a global convolution. And that allows it to directly copy the useful informations to the output. But in selective copying, the input is a randomly spaced useful information and noises. The important thing here is the intervals between the noises and the useful information are random. So in order to get the correct information copied to the output, the model needs to learn which information is important and which information is not important. But in S4, there's no such filtering mechanism. So it will just treat each input information as the same weight. So that this in the selective copying task, S4 will fail. Another task is the induction heads task, which is the one important feature for transformers. This task means you have a sequence of input information, and as the output, you need, like, given a in this case a black box, you need to infer in the context what is right after the black box. That requires the model to look back into the context and find out the important information and infer what is after it. And also because of S4 they set a global weight, the same weight for every single input. So they cannot go back into the context and select the next information that is useful. So the author made a very important statement that they say the fundamental principle of building sequence models is selectivity. And this is a visualization to separate different models based on their state sizes. On the left-hand side is a RNN, which has a small state size. This ensures RNN and S4 to be more efficient, but because the state size is small, it is less powerful. And on the right-hand side is a transformer. It has a very large self-attention matrix with no compression of the context. So that enables the transformer to be very powerful, but it's also less efficient. Mamba lies in between those two. It has a relatively small state size because it compressed the context selectively, but also because the information is selectively compressed, it's more powerful. And because the small state size, it is more efficient. And this compares S4 and the Mamba side to side. On the left-hand side, the S4 is given an input X, the output should be Y, and all the A, B, C, and the step size parameters are fixed after training. This is, yeah. So this is a linear time invariant model. And S6, instead, just making a little sweet tweak by setting the B, C, and step size parameters, they can change based on the input. That's how they can, like, given a input, they can modify their B, C, and step size matrix to better distinguish which information should be preserved and which information should be discarded. And one small question is why A is not parameterized by the input. That is because I need to go back over here. Remember, we've discretized from the continuous form from the A matrix to the A bar. There's naturally a step size parameter here that controls how the discretization works. So it's redundant to set the matrix A to be a parameter of the input because the step size itself is included in the discretization step, so that A no longer needs another step to be parameterized on the input. All of this makes this model time varying. So we can only enjoy the recurrence properties of the Mamba only. So it comes with a great cost. The Mamba moves from the linear time invariant system to a time variant system, meaning that the parameters are now dynamic based on the input, so that we can no longer represent it as a convolution. So it lost training parallelization. However, the authors discovered that they can use parallel scan, also known as prefix sums algorithm, to use the modern GPUs to realize the parallelization. The parallel scan or the prefix sum algorithm is visualized a simple example here. So the goal is to compute the cumulative sum of a input sequence. So for example, here, the input is from V0, V1, all the way to V7. And we want to know is the cumulative sum, like V0 plus V1, V0 plus V1 plus V2, and etc. This is all done building a binary tree, so that we can compute the V1 and V0 first, and V2, V3 together, V4, V5 together, V6, V7 together. So this, we can use 4 GPUs to do that, so that this part is parallelizable. And building the binary tree all to the top, so that we have this intermediate cumulative sum representation. And then we do a downsweep, basically, to recover what is the intermediate cumulative sum. So at the end, this parallel scan algorithm can greatly reduce the computation. all of this parallel scan algorithm is built upon the assumption that the computation is associative, which means that like A plus B plus C, it doesn't matter you compute A plus B first or you compute B plus C first. They can happen, like the order doesn't matter. And thankfully, SSMs, the transition of SSMs are associative. That's why we can use the parallel scan to parallelize the training process. Maybe I'll skip the proofs of parallel scan. Yeah.
Are you doing something about the event?
Yes.
Main thing is how did they apply to the event?
Yep.
It's very important first.
Yep. I'll skip this perhaps. Yeah, so this is the overview of Mamba. It's compared to S4, it adds this little blue part. So that B, delta T, and C matrix are all based on the input. Okay, finally, applications. So in the first paper, Scaramuza group's paper, the state space models for event cameras, I think this is maybe the first paper. Okay. So the motivation is that, remember the arbitrary step size? The SSM can be transformed from a continuous to discrete time system with arbitrary step size. What does it mean?
What did they apply in each province?
So,
Which task?
in let's see. Is this segmentation? I think it's segmentation task. But anyway, they try to solve the problem that when we're training a model using a sensor that, for example, is the sample rate is 20 hertz. And after that, we want to apply it to a sensor of 60 hertz. The model will no longer work because it's a different domain for the model. But for the state space model, because it is defined firstly in the continuous domain, and we can choose the arbitrary step size, then the state space model can deploy at a different frequency with minimal loss to the performance. So if you're training like a flying drone, trying to avoid the obstacles in the room, and you're using the 60 hertz RGB camera to train the model, it will work. It will still work in the test when the sensor is 60 hertz, but when like perhaps you use a newer sensor that is 120 hertz, it will just fail. So this is their architecture, which is their input is just event frames. It's image-based input in this paper.
So time surfaces or event?
No, even more simpler.
Event counting.
Yes.
Okay.
Their architecture is
over event count images over a certain time interval or
yes,
over a certain amount of events to compensate.
Over well,
okay.
I don't remember.
I'm just asking because you say.
I'm real curious too.
Because you say they can compensate, they are frequency independent.
Yes.
Okay, so how do they do that? Yeah. Okay.
I'm not sure. I remember there's a small paragraph.
It's like a small piece.
Yes, very small.
Anyway, so you take a slice of event, you pin it in one image.
In 0.1 seconds, the experiment so far is like 0.1 seconds till like 1 millisecond. Okay.
Okay, time slice, you make it an image and then
this is all like I don't see as a novel architecture because it's just apply the convolution and multiple MLPs, and the block assay and the grid assay is just feature extraction from the local and the global size.
Okay, but
So-
what's state space model applied to the taking the whole frame and then doing the SSM over the frames? Or it's over?
It is processing the features output by this VIT.
Oh, so you first take the image,
Pass it to a VIT
pass
and
it to a VIP, out you get now features.
features, and the SSM applies to those features.
Okay, so the VIP provides you features over what? Over volume? Bunch of features over volume?
I think it's-
over slice or?
I think it's 2-channel event image.
Okay.
I remember it is.
You pick a slice and the VIP gives you for that slice features.
Sorry?
Yeah, image. Yeah, so it gives you features for one slice, like an image, and then you take the next image, get features. And then you apply this is the state space model over the features
Yes.
over a certain amount of time.
Yeah. It is a very strange representation.
It's the VIT because the state space models doesn't have many layers as such, right? Like it is like you have for me it is like one layer applied over time because you have the same A matrix and then PC, but you still want like good features, high dimensional features from your thing. What I'm assuming is they use like slices over time and then use them as images.
Okay, but the VIP provides features over each slice.
Mm.
Yes.
Can the VIP also provide features over video? No, it's always over.
Not a VIP, but there's the video visual.
Oh, video, okay, but this is just vision transport, okay, so you
Mhm.
get okay.
You know if do they train in the FT or they either pre-train them?
I don't know, honestly.
Okay, I'm just wondering, now you have the state space model, really frame over a certain amount, and then you take the next block of frame, so what can you do with it, with such a representation? I mean, maybe action representation, you should. But what are you doing?
Before I talk about the performance, I want to, I think this is their real novelty here. They designed a low pass filter on the matrix C, which we don't talk about before. The C matrix translates the hidden space to the output. And the authors observe that some states in the state space are oscillating extremely fast, so fast that they exceed the 2 times the sampling rate, which is the Nyquist frequency. So that causes aliasing, which means those states are no longer reliable and we should not use them. So that's why the authors create a masked version of C matrix to kill those states whose frequency is above that threshold. So essentially remove those fake information from the computation. And what they're testing, I believe they are training on the 20 hertz scenario and testing on the 4080, 120, 200 hertz. And by using a S5 module, there's very little decrease performance drop. Hmm?
Yeah, okay.
Like
This is the state space model trained on.
Like the data?
But the task,
Oh,
you must have a goal to apply the state space model.
I think you're doing student classification on the Gen 1 automotive data set.
Image classification.
that is
slice.
another table. This table is,
Oh.
I think it's
okay. But
segmentation.
this is the table from the Scarabins paper, right?
Yeah,
It is or not?
it is.
Oh, okay then.
Somewhere, I think the task was like reconstruction of the info.
Reconstruction.
Yeah, like
Gen 1. Yes.
there was a slide where like
Gen 1 is
direction,
But that object protection.
Oh, it is. Yes, yeah.
You're there.
You're comparing it to YOLO.
Okay.
This is the Gen 1 automotive, so there's
So I
a
think-
bunch of bounding boxes of pedestrians and cars. So they're trying to.
Yeah, so these numbers are mean average precision, like between two bounding boxes. And RVT and GET here are both transformer-based, purely transformer-based models. And this model, I assume, is the SSM VIT here. So yeah, SSM
So when
does
you
is
learns the bounding boxes, coordinates, okay.
Yeah, Y is the one, yeah.
Hmm.
This is pretty cool actually, like the fact that the performance doesn't drop over different frequencies. I think this is very interesting because now you can apply this over different environments. So like you train on like certain environments, but even on other environments where the frequency is very high or low, you can just, it seems like you can use this right out of the box.
But
Yeah,
bounding box is actually that the more does, it's spatial class. YOLO is YOLO is done on one frame, so what is the state space model doing here? It memorizes where the object was before or what?
And I'm assuming the bounding box also moves.
But
yeah, but still the bounding box.
Yeah.
Yeah,
It's a spatial.
yeah, I don't get that, okay. Wait.
It's just a feature instruction. Does have any.
The feature extract, but the features are extracted by VIT. Or at least the features are extracted via.
No, it's not, it's integrated. You can see the structure. It's just.
So the state space model is part of the VIT.
Yes,
Oh, okay, you're with that, okay.
and then they use.
Okay, so the state space model is going already over space and time.
Yes.
Oh, so it's running with three-dimensional.
So,
Can you
yeah,
go
so everything before SSM is just feature extractor and that's it handles the spatial temporal feature.
I see, okay, so you extract features, but then you run the SSM three-dimensional. Like you do it via the piano curves, okay. Okay, that's something.
And then it looks like,
Oh, okay.
and then it looks like they take the features from the SSM, they put it through a YOLO detection head. So that's actually for the bounding box. Yeah, it's just YOLO detection head, it's just. Yeah.
just a task hat.
Yeah.
But you're still frames.
Yeah, that will be the end of my presentation.
Thank you.
Thank you. One thing I want to mention that is that the following papers I didn't present here. They process events as point-based, which means that the X, Y, and T are directly inputted into the state space model.
Which ones you said?
There are two. There are two.
The event Mongo is.
The event Mamba. Yeah, the event Mamba is this one.
Yeah.
Is point-based, and later the pre-Mamba, the deraining one, that is also using a state model without the VIT part. So that hints, I think that gives us a hint that maybe SSM can directly process the event streams like without any without yeah, like VIT, yes.
Well, but then we have a lot of states if you click each event. Okay.
Yeah, but I mean, I think in event Mamba or the pre-Mamba even, I think they like drop a lot of the events. Too.
Or you sample events,
Yeah.
and then again you run this tree curve to connect this
Yeah.
model. But when you run this 3D curve, then you have to still pick the size of the time, right? The time slice, and then the next time slice. It's just a longer time, right? Yeah. All right.
Yeah, my question is the time slice always fixed length? So during one run, so you use that, it can be configured to run on different slides, like during one sequential run, and you input like 30 milliseconds and then a different one.
That's a good question that I don't know the answer.
You're talking for this paper?
Yeah, yeah.
Yeah, I think they keep it consistent.
Mhm.
Yeah, they keep it consistent.
They were working on the levels, but we have a table of zeros.
Okay, maybe just what do they do in event number? Okay, fine, fine, all right. Okay, but you went to what?
Audio reconstruction. And it didn't work.
What
reconstruction say?
audio reconstruction from events, yeah.
Yeah, so,
Yeah, how did it work?
but also I guess I didn't have.
Substances by. Okay, all right, other questions? Would you like other questions online?
They have different frequencies, but like every time they test the different frequency, it's consistent.
So I'm thinking, can we make the asynchronous? OSDM and kind of synchronous, means you input like frames, features, slides.
Not using.
Okay, so I would aim to.
You mean variable length input?
Yeah, very, yes, yes.